Good day, everyone. I'm recording this video today because I think I'll be out for B days here. A days, if you're watching this, well, good, then you're just reviewing chapter 15. Otherwise, B days, hello, and also get out some notes because we have to do chapter 15.1, which is called Central and Inscribed Angles today. So to start out, we have about 3 vocabulary words. We have a chord, which is a segment whose endpoints lie on a circle. And we'll look at that in just a second. We also have a central angle, which is an angle with measures less than or equal to 180, whose vertex lies at the center of a circle. And we have an inscribed angle, which is an angle whose vertex lies on a circle and whose sides contain chords of the circle. Okay, so that's a lot to unpack, but one big difference we should note is that the central angle has a vertex at the center of the circle, that little corner of the angle, this part right here, that is at the center of a circle, whereas an inscribed angle, it is on the circle. I'll show you what I mean by that in a second here. So here we have a diagram specifically looking at chords, central angles, and inscribed angles. Well, before we even look at that, let's talk about different words, the other words we're familiar with. One word we should be familiar with when it comes to a circle is the center. One word we should be familiar with is the radius. And one word we should be familiar with is the diameter. Okay. Well, just real quick, get you the overview of what those are. The center is the center of the circle. Ta-da! The next part here is that we have a radius. A radius is from the center of the circle to an endpoint on the circle. And then finally, the diameter is going to be going from one endpoint on the circle through the center and to another endpoint that lies on the circle. Okay? You'll notice that half of the diameter is the radius here. Okay? So, now that we've known this stuff, let's go and talk about chords. Well, AB and BD, it tells us that those are chords. So AB, A to B here, this segment right here, and BD. Okay, so, or on this one, on the right here, it's the same deal. They're just different chords. So AB and BD are chords. The next part here is a central angle. Well, remember, a central angle is an angle whose vertex lies on the center. Well, in this case, it tells us that ACD is our central angle. And therefore, we have this angle right here being our central angle. We're going to learn a cool relationship here between the inscribed and the central angle. Okay, well, it also tells us on this one that the same deal. ACD is our central angle. You'll see that both of these angles in both of these figures are less than 180 degrees. Okay? So when we're talking about the central angle, we're talking about the angle that is less than 180 degrees. Okay, finally, we have something called an inscribed angle. Now remember, I told you that the inscribed angle is the angle whose vertex lies on the circle itself. So again, that point of the angle lies on the circle. So ABD is one of these, and ABD on this right figure is also one of these. This inscribed angle here, remember, is also just going to be, you got to kind of see the difference here between the central angle and the inscribed angle. The central angle lies on the center. The inscribed angle lies on the circle. Okay? So that's one big difference that you'll need to kind of come up with. Let's move on. So one thing we also need to know is that if I add up, so if I go back here and I take this central angle, ACD, and I add it to other central angles, and I add all of these central angles up, well, I should end up with a number. I'm going all the way around the circle, and so our magical number here is 360 degrees. All right. So you could write something along the lines of the circle is 300. When I add up all the central angles, is going to equal 360 degrees. But realistically, like if you just add up all of the angles of a circle around a circle, that's going to be 360 degrees. Keep in mind that this does not work with intercepted angles. So angles that lie on the circle itself, we have different rules for. So something like this and something like this is not going to suddenly equal 360 degrees. In fact, we learn special relationships about all these angles when we get to chapter, let's see, I believe it's chapter 15.2. Okay. So just kind of hang in there for now. Here we have something called a minor arc, a major arc, and to some degree we have a semicircle. All right. The minor arc is an arc whose points are on or in the interior of a corresponding central triangle. Okay. Sorry, not central triangle, central angle. So here, when it talks about arc AB, that's what this kind of curvy symbol above AB is. This is talking about the arc from A to B. This is what we call a minor arc. A minor arc is going to be, well, a minor arc is only going to have 2 letters. And the reason it has 2 letters is because it takes the shortest possible route to get to from A to B, right? Another thing we'll notice about the minor arc is that the minor arc, the measure of it, is going to be equal to our central angle, ACB. So, for instance, if ACB was 40 degrees, the measure of our arc AB is also going to equal 40 degrees. Okay. The major arc is an arc whose points are on or in the exterior of the corresponding central angle. So for instance, you'll see that I represent the major arc with 3 letters. And the reason I do that is because I need to know what direction I'm going to. If I don't give a direction here, I have no idea that I'm talking about the big way or the longer way around the circle rather than the shorter way. If I gave you, again, something like from A to B, but I want you to go this way, there's no distinction here between me going clockwise and counterclockwise. That's why we add the D in here. The D is going to tell us, hey, this is the major arc. It's the major, bigger. And so we have ADB being our bigger of the 2, right? So the measure of ADB, or arc ADB, is going to equal 360 minus the measure of angle ACB. Okay. So in this case, we could call this one 40, again, 40 degrees. I could take 360 minus 40, which is 320, and that would equal the measure of our major arc. Okay. So this would be 320 degrees. The only difference with a semicircle is, again, we need that direction. So we need to be following a direction on the semicircle here. And that measure of the semicircle, well, a semicircle is half a circle. If the whole way around a circle is 360 degrees, how much is halfway? Well, it's 180. All right. So feel free to pause the video here, kind of let the class catch up with writing this down and taking notes here. And then when everyone's ready, let's move on. All right, so let's move on here. One of the things that we talked about the angle addition postulate. Well, the arc addition postulate is very, very, very similar. If you remember at the beginning of the year, I told you something along the lines of if we take angles and we add them up, that the two smaller angles is going to equal the bigger angle. So if I take an angle like that and I split it into two parts, that these two smaller angles here are going to equal my bigger angle. Well, the same thing is apparent with arcs. If I take ADB, so if I have this big arc here, ADB, and I cut it into two parts, if I add those two arcs together, it will equal my larger arc. Okay? And so that is the arc addition postulate. One of the things we can infer here is that there is technically also an arc subtraction postulate. And all we're going to do to the statement above is we're going to subtract, say I'm solving for the measure of AD, arc AD. All I need to do to both sides is subtract arc DB. Okay? Subtract the measure of arc DB. And you'll see I put DB and then I draw the arc above it. Okay? And basically what I'll end up with is the measure of ADB is equal, minus the measure of arc DB is equal to the measure of arc AD. Okay? So again, that arcs are on there. I'm going to draw those in. Again, feel free to pause the video, kind of have people catch up on this, and then let's move forward. All right. So one of the last big slides that we're going to look at today is the inscribed angle theorem. The inscribed angle theorem says, well, first we have to know what an intercepted arc is. The intercepted arc is basically the arc that corresponds with an inscribed angle. Okay? So remember the minor and the major arc, those were for central angles only. Now that we're talking about inscribed angles, we're actually talking about this arc right here, AB, that's our intercepted arc, and angle ADB, that is our inscribed angle. The relationship, or the inscribed angle theorem, says that the measure of an inscribed angle is equal to half the measure of its intercepted arc. This is essentially saying that whatever AB is, whatever degree measurement AB is, this intercepted angle is going to be half of it. Well, let's say that AB is equal, this arc AB is equal to 50 degrees. Okay, so arc AB, measure of arc AB, not angle, AB with an arc above it is equal to 50 degrees. Well, ADB, measure of ADB, is half of the measure AB. So the measure of this angle right here, ADB, A to D and D to B, is going to give us this arc, little arc in here. And we're going to be given angle ADB is equal to half of whatever arc AB is, half of 50. And so the measure of angle ADB is going to equal 25. Something really cool to note is that as long as we share the same two endpoints, our angle's always going to be 25. So let's pick a different color here. Let's do red. If I have a vertex right here, you'll note that that angle, let's call this Q, this point Q. That AQB is also going to be 25 degrees, right? Because this is an inscribed angle. The inscribed angle is half of the intercepted arc. Okay. Let's look at a couple questions today, a couple examples. Ooh. Again, feel free to pause the video, let people catch up on this, and then let's continue. All right, so let's move on. Here's an example that you might look at. We're trying to find X, Y, and Z. All right. It tells us that segment AD is a diameter. We want to find the values of X, Y, and Z here. One thing I noted earlier is that the arc measurement in our previous slides was equal to our central angle. Well, essentially, that just tells me that, again, that last slide is talking about intercepted and inscribed angles. But if we looked at the minor arc, major arc slide, if you look back at your notes, you'll note that those angles are just equal to the arcs. So in this case, we have that X is equal to 25. It's equal to our arc because it's a central angle. Same thing with Z. Z is an arc, and we have our central angle, which is 55. So Z is going to equal 55 degrees. And finally, Y is right here. It kind of hides it for whatever reason. I don't know why it turned that color, but Y is going to be some degree measurement. And the way we're going to find that is we are going to have to know what the degree measurement of half a circle is, because AD is our diameter. It splits our circle in two. Well, if you remember, it's 180 degrees, which means if I add Z, or this 55, and I add this X up, and I subtract it from 180, I should be able to get my Y. So let's do that. I'll take 180. There we go. And I'll add 25. And I'll, subtract 25, and I'll subtract 55. So 25 minus 50, or negative 25 minus 55, that's going to be 180 minus 80. And I should be left with 100 degrees. And that will equal Y. All right. Well, let's check our work. Check it out. Looks pretty spiffy. All right. So let's go on to our next example here. Feel free to pause the video when you need. We'll continue on. So find the measure of each arc. There's a crucial thing about going around a circle. And going around a circle, we know that it's 360 degrees. So if I add up all of my central angles, that's the sum theorem from earlier. if I add up all of my angles in a circle, it should equal 360 degrees. Okay, so let's add it all up. If I do that, you'll see that I essentially, let's work that out real quick. If I have 4x plus 3x plus 3x plus 2x plus 2x, well, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I'll kind of put another step in here. So that's 14x. And then plus 10 minus 14. That's going to be minus 4 equals 360. All right. And then right below that, I'm going to keep it going. I'm going to add 4 to both sides, and I'm going to get 14x equals 364. All right. Then I divide both sides by 14, and I get 26. Well, if I plug that 26 in for every single one of these angles, you'll note that I'm going to get in respectively 104, 78, 88, 52, and 66. Particularly, that is going to go right 4 times 26. That's going to be 104. 2x minus 14. Let's see. I believe that one is going to be, let's see, 26 times 2. 26 times 2 is going to be 56. Nope. I need my calculator. Ooh. 52. 52 minus 14. It's going to be 38, I believe. 2x, 2 times, that's going to be 52. 3x plus 10, that's going to equal 3. That's going to be 3 times 26. That's going to be 78 plus 10. That's going to be 88. And we just found out that 3 times 26 is 78. All right. You'll notice that for whatever reason, I might have left out this 38 here. Must have completely forgot about it. But make sure you're trying to solve the entire question. Teachable moments. All right. Well, let's continue on here. An inscribed diameter. If there's an inscribed angle theorem, there's most definitely an inscribed diameter theorem. Well, again, if I find the center of my circle, let's say our center is about right here, okay? And then I draw a diameter through that circle. It doesn't matter what point I'm on as long as I go through it. And the inscribed diameter, so if I draw an inscribed angle now, I pick a point on the circle. Inscribed angle is a point on the circle. Central angles is the center. So let's pick that point right there. And I draw to the end points of this diameter. You'll notice something kind of weird. Remember that the inscribed angle is half of our arc. Okay, so this arc is a semicircle. Okay, a semicircle, well, that's going to be 180 degrees. Remember, half a circle is going to be 100. This arc right here, or this arc even all the way around it, it's 180 degrees. And this intercepted arc right here is going to be half of that. And so this angle right here is a half of 180, which is 90 degrees. So you'll notice that the intercepted arc of a diameter is going to be 180 degrees, as well as the intercepted angle with endpoints lying on a diameter is also going to be 90 degrees. This is what we call the inscribed diameter theorem. Let's do one more set of examples here. Then you should be freed up to start up on the homework today. So we have a circle. We're going to call it circle C. The C stands for that center there. And we are given arc DE. Okay, the measure of arc DE is 84 degrees. That means that this arc from D to E is 84 degrees. Which means that I want to find the measure of angle DGE, but I want to find the measure of angle EFD. Okay. Let's start with DGE. So let's choose maybe blue, a nice blue for angle DGE. D to G and G to E gives us DGE, which means we're talking about this inscribed angle. Remember, inscribed is the angle whose vertex lies on the circle. Well, we're going to have to use the inscribed angle theorem. Remember, the inscribed angle theorem here says that if we have an inscribed angle, that the intercepted arc, in this case that's DE, is half of, or 1/2 of the intercepted arc is going to be our inscribed angle. Okay, 84 is our intercepted arc. Therefore, half of that is going to be our inscribed angle. Well, if I was to write that out, this would look something like half of 84 is equal to, that would be 42. And therefore, our angle here would be 42. Okay, well, let's think about that again. You'll note here, now it wants us to find EFD. Well, EF, F to D, we're talking about this angle right here. Well, that's just another inscribed angle. And what you'll notice if you were listening earlier is that I said if they share the same endpoints, it doesn't matter. That angle is going to be the same no matter where I put it on this circle. Which means that if I have intercepted arc DE being 84, that angle EFD is going to be half of that again, which means that angle EFD is going to equal 42 degrees as well. And you could write out half of 84 again, or you could just write the 42 here. Okay. All right. We got 3 more to go, and then we're good to go here. So the center of the circle is A. We want to find each measure using the appropriate theorems and postulates. So let's start out with arc CE. Ooh, that one's kind of a pretty quick one. Remember, if this angle right here is 51, and it's a central angle, the arc itself, CD, is also going to be 51. And therefore, this box right here is 90. So the measure of arc CE is going to be 51 plus 90, which in this case is going to equal 141 degrees. Okay, well, let's do the same thing here with DF. Well, let's think real quick. We know that, perfect. So we know that FC, it looks like a diameter. Okay, I'm going to say that it is. So that we have 90 and 51, and we have this angle right here, and we need to know that in order to find DF. So we actually need to know EF first. So let's write that out. Is that we know the measure of arc EF plus the measure of arc ED is going to equal the measure of arc DF. All right. And so we have that EF, well, I know that 51 plus 90 plus whatever this angle is going to be is going to be 180. It's half a circle. So that was 141, if you remember from earlier, CE. Let's take 180, subtract 141, and that will give us 39 degrees. So this right here, this EF, this arc EF, talking specifically about this arc right here, is 39 degrees. Also meaning that the central angle is 39 degrees, but we'll pocket that. And so we have EF and ED. Well, EF is going to be 39 degrees. We have ED. ED is 90. And therefore, we have that the measure of DF is 129 degrees. Okay, there we go. There's our second part done. Lastly, we have the measure of arc BEC. So again, starting at B, and I'll even use, let's go crimson. Starting at B, going around the circle, I want this arc going through E and stopping at C. Okay, well, I already messed up for one, because I went from B through C and stopped at E. That's not what this is asking. It's asking me to start from B, go all the way out through E, and stop at C. So what it actually wants is it wants this big major arc. Well, remember that this looks like a diameter. This one, I'm going to say, also is a diameter. And therefore, we can use vertical angles here to state that arc BC is 39 degrees. Therefore, the angle BAC is 39 degrees. Okay. So if the round the circle is 360 degrees, and I know what this smaller minor arc is, I can take 360 and subtract our minor arc to get our major arc. If I take 360 and subtract 39, I should get 321 degrees. Okay. So that's the end of the video here. Feel free to pause here again. Once you're done, I'll make some quick announcements. Kids, thank you again for, please be good for the sub while I'm gone. That's always my expectation. Please don't leave a bad taste in the sub's mouth. That is going to be a big no-no. So make sure you're finishing the chapter 15 vocab by today. Just for people on April 18th. And then also make sure that you're working on this for the rest of class. Volume shouldn't be anything bigger. If the sub has to tell you 3 times to quiet it down, please don't let them do that. If I get a sub note about that, it's going to be a bad time. Additionally, please make sure you're working diligently. If you need more examples on this, you can go to module 15.1 in your book, okay? Or you can go back in your notes and review some of these examples as well. Make sure you're behaving, and make sure you get the chapter 15.1 homework done. Thank you very much. I hope you all have a great day. And I will hand back your quizzes when I get back. All right. Have a great day. Goodbye.